In this video, we discuss annuities. What do we mean by annuity? Annuity is a sequence of payments made at regular time intervals, and these are called terms. Examples of annuities: regular deposits to a saving account, monthly home mortgage payments, monthly insurance payments, retirement payments, or these are examples of annuities. And here we focus on ordinary annuity. Ordinary annuities mean that payments are made at the end of each term. For example, if you pay monthly, then you pay at the end of each month. And we also focus on certain and simple annuities. By certain annuity, we mean that the term is given by a fixed time interval. And by simple, we mean that the payment periods coincide with the interest conversion period. We denoted this as M. Okay, so we study annuities with the following conditions. First, the terms are given by fixed time intervals, and that means it's going to be certain. The periodic payments are equal in size, and the payments are made at the end of the payment periods, and that means it's going to be ordinary. The payment periods coincide with the interest conversion periods, so these are simple annuities. So let's start with the future value of an annuity. So we want to know how much money would you have after specific time: 1 year, 2 years, 10 months, etc. So if you are paying for retirement, you put a certain amount of money every, say, a month, and let that money grow over time. So here we have this formula that gives us the future value of an annuity, where R is the payment that you make in dollars, and I is the ratio R over M, where R is the interest rate and M is number of conversion periods. N is number of payments. Now, how do we get this formula? So the derivation of this formula, just an explanation of how we got this formula. So imagine that you make payments of $100 at the end of each quarter so you pay quarterly over a period of 3 years. And suppose that account earns interest on the deposit at the rate of 8% per year, compounded quarterly. So in this case, we have the following timeline. One year, 2 years, 3 years, and we make payments every 3 months. So here we pay $100, $100, $100, and so on. Okay, So let's start with the first value here, first payment. So when you make this payment, you ask yourself how much this worth at the end of the 3 years. So in order to find that, we apply the compound interest formula. The compound interest formula says A equals P times 1 plus I, or raised to power n, where n is M times T, number of convergent periods, times time in years. So let's apply it here. We have 100 times 1 plus, what is I in this case? Now I is R over M. R is 0.08 because it's 8% over M, number of convergent periods. We have 4 convergent periods a year because it's compounded quarterly. So this gives us 0.02. This is the value of I. Or raised to power 11. How many payments or how many periods or terms are there for the first 100? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So 11 terms. And for the second one, for 100, we have 100 times 1 plus 0.02, but we have 10 periods. For the third one, we have 100 times 1 plus 0.02, and you have 9 periods, and so on. This one has 100, 1 plus 0.02, and just one period, one term, and the last one doesn't have any term. So at the end of the last term, you just pay 100 and that's it. So we can write 100 times 1 plus 0.02 raised to power 0, because this raised to power 0 is equal to 1, and that means we got 100. Now to find the future value, we need to add all these values, because it's not, if you want to find the future value, it's not just finding the sum of the hundreds, because you have interest. So we have to add these values here. Now to find the sum of these, we have the future amount. It's equal to 100. Let's start. Okay, so let's start from right to left, from here, from the last value. So you have 100 times 1. Let me write 1 plus 0.02 as 1.02 raised to power 0, plus 100 times 1 plus 1.02 power 1, up to 100 times 1.02 to the power 11. So the sum of these, instead of finding the sum by adding all these values, we can simplify, make some mathematical simplifications. So let's take 100 as a common factor, and let the first term, 1.02 raised to power 0 is equal to 1. Any number raised to power 0 is equal to 1 except the 0 itself. So we have 1 plus. Now if we take 100 as a common factor, we are left with 1.02 to power 1 plus then 1.02 to power 2 up to 1.02 to power 11. Now if we look at this expression inside the brackets, we find that this is a geometric series, and the geometric series is a mathematical concept. For geometric series, we have, let me give you an example of what we mean by geometric series. Geometric series is a series with a constant ratio between successive terms. For example, if you have 2 plus 4 plus 8 plus 16, etc., and you want to, this is a geometric series, Now this is a geometric series because if you divide each term by the previous one, for example 4 divided by 2 you get 2, and 8 divided by 4 you get 2, 16 divided by 8 is 2, and so on. So as you can see, we have a constant ratio for all these fractions. So this is a geometric series, we call it geometric series. Same thing here. For our example, we have 1 plus 1.02 plus 1.02 raised to power 2, etc. So if you divide the second by the first, you get 1.02. The third by the second, you cancel this with this and you get 1.02. You still have same ratio. This is called ratio, denoted as R. Okay, so this is a geometric series. This is what we mean by geometric series. Now for finite geometric series, we have the following sum. Instead of finding the sum by inserting this or adding these up, we can find the sum of this series by applying the formula S equals, the sum is A times 1 minus R to N to power N over 1 minus R, where R is the ratio and N is number of terms, A is the first term. Now here we have S equals, what is the first term of this geometric series? It's 1 times 1 minus, what is R in this case? The base, the ratio is 1.02. This is the ratio. Raised to power N, how many terms are there? From 1 to 1.02 raised to power 11, we have 12. We have 12 terms, all divided by 1 minus R. R is 1.02. Now we have, now this is the sum. This is the sum of the geometric series, but this is multiplied by 100. So we write 100 times this S. So times 1 minus 1.02 raised to power 12 over 1 minus 1.02. Now just for purposes of finding a formula, let's switch these because 1 minus 1.02 is negative. We don't want to get negative here. So, and for purpose, as I mentioned, purpose of finding formula, I want to switch these in the denominator. But if we do that for the denominator, we should do the same thing for the numerator. So we have 100 times 1.02 to power 12 minus 1 all over 1.02 minus 1. Now from this we can get a formula. So 100 is R times, what is 1.02? 1.02 is 1 plus I. So 1 plus I raised to power N, 12 represents N, minus 1 over 1.02. 1.02 is 1 plus I, minus 1. 1 minus 1 is 0. We are left with I. So we obtained the formula here. Okay. So this is the future value. Now let's take some examples. The first example here, we want to find the future amount of an ordinary annuity consisting of 12 monthly payments of $100. This is R and this is N, and the interest is 12% per year. So we can find I by writing I equals R over M. R is 0.12, which is 12%, and this is compounded monthly. So in 1 year we have 12 months, so I is 0.01. Now we apply the formula. S is 100 times 1 plus I is 0.01 raised to power n minus 1, all divided by I is 0.01. Now using calculator we get 1268.25. So another example. Now Phyllis opened an IRA on January 31st, 2015 with a contribution of $5,500. This is R, and she plans to make contribution of this amount thereafter on January 31st of each year, so at the end of each period, until her retirement in the year 2034. So we have 20 payments here. This is N. If the account earns interest at the rate of 4% compounded yearly, so I in this case is R over M. R is 0.04 over M. M in this case is 1 because it's compounded yearly. That's equal to 0.04. So we want to know how well, this is a keyword, how will Phyllis have in her account when she retires. So this is a future. We are asked to find the future value. So S in this case is 5,500 times 1 plus I is 0.04 raised to power n. N is 20 minus 1 over I 0.04. Using the calculator we get 163,779.43. So this is the amount Phyllis will have in her account when she retires. Okay. Now the second part of this section is about the present value of an annuity. So we want to determine the current value P of a sequence of equal periodic payments made over a certain period of time. So we want to know the current investment value. So the amount P invested now and earning interest at the rate I have accumulated value of P times 1 plus I to the power n. I want to derive this formula. So the amount P interest invested now and earning interest at the rate I have accumulated value P times 1 plus I raised to power n. This is the compound interest. But this must equal the future value of the annuity at the end of n periods. So this equals R times 1 plus I raised to power n minus 1 over I. So this is the key step here. Now we solve for P. In order to solve for B, we need to divide by 1 plus I raised to power n both sides. So we divide both sides by this. We get P equals R over 1 plus I raised to power n. Let's split this into two expressions or fractions. 1 plus I raised to power n over I minus 1 over I. And then just to simplify the result. Now we multiply this denominator by the other two denominators here. So we have r times 1 plus I to the power n over, now when we multiply the first by the first denominator, we get 1 plus I to the power n times I minus 1 over, now we multiply the second denominator by 1 plus I raised to power n all times I. Now let's simplify more. We cancel this with this, and we get r times 1 over I minus 1 over 1 plus I raised to power n times I. Now let's bring this up here, and when we bring this up, we change the sign of the power, because if you have in general 1 over x to the power n, when we bring this here, it becomes negative n. The power becomes negative n. So this is one of the rules of powers. So we have r times 1 over I minus 1 plus I raised to power negative n over I, because we still have I in the denominator. We didn't bring it up. So we have r times, now we have a common denominator I, and in the numerator we have 1 minus 1 plus I raised to power negative n. This is called the present amount or present value of an annuity. So this gives us the current value of an investment. Now let's take some examples. The first example, we want to find the present value of an ordinary annuity consisting of 24 monthly payments of 100. So this is R and this is N, and the interest rate is 3%. So from this we find I equals R over M. R is 0.03 over M. Since this is compounded monthly, that means M is 12. So this is equal to 0.0025 if you use the calculator, or just simplify this, you get 0.0025. Now we apply the formula. The formula is P equals R times 1 minus 1 plus I raised to power negative n all over I, and this is 100 times 1 minus 1 plus I is 0.0025 raised to power negative 24 all over I, 0.0025. Now using the calculator we got $2,326.60. The last example here is the Denver Wildcatting Company has an immediate need for a loan. In an agreement worked out with its banker, Denver assigns its royalty income of $4,800 a month for the next 3 years. So this is T, and this is R, from certain oil properties to the bank, with the first payment due at the end of the first month. At the end of the first month, that means it's certain. That means it's ordinary. If the bank charges interest at the rate of 6% per year and compounded monthly, so here we can find I is R over M, 0.06 over 12 because it's compounded monthly. So we want to know what is the amount of loan negotiated between the parties. That means we're asked to find the present value. So the present value is equal to, so we want to find the present value of this ordinary annuity. P is 4,400 times 1 minus 1 plus I. I is 0.005 raised to power negative 36. Why? Because here we have n. This is n. N is m times t. M is 12 and t is 3 years. So number of conversion periods is 12 and number of years is 3. So this is 36. All divided by I is 0.005. Computing this using calculator, we get 157,780.88. This is the amount of the loan negotiated. It's in dollars for sure.